All right, everyone. Welcome back to Legion School. So I'm taking over today for Sean. Sean has promised me that he will be back on Wednesday to do his next low-level runtime session. Today, what I want to do is continue talking about the shape of region trees, both index-based trees and region trees, talking about how those nodes get instantiated. We're also going to start looking at how we manage some of the state region trees just to see what those data structures look like so you can be familiar with them for when we start talking about the analyses that we're going to do over region trees. And then later what we're going to do is hopefully we'll have some time how we track which region trees we know exist on different nodes across the system. Okay, so let's start off reviewing just very briefly where we were last time and what we were doing, and then we'll start looking at region tree nodes and how they get instantiated. Okay, so I'm going down here to region tree.h just to remind everybody where we started the last time. Let's see here. Here we go. Okay, and so if you recall the last time, we spent most of the time looking at how we created both index-based nodes. So here's the class for index-based nodes, and we're also looking at index partition nodes. And we went over both of these classes, and we looked at how they get instantiated from the actual Legion runtime. And so today, what I want to start off doing is actually looking at how we instantiate region trees instead of just index-based trees. Okay. So if we jump back here to legion.h, let's actually trace through one of the calls to create a logical region. So everyone who's used the runtime API knows there is a create logical region call. And what you'll notice is that we pass in two things to this create logical region call. Technically we're passing three, including the context, but we're passing in an index space and a field space that are going to be, we're going to take the cross product of those to generate a new logical region. And one important detail of the runtime is that what we're going to see is that we actually, every time you do this call, you're actually going to get a unique logical region back. And therefore, the logical regions are actually going to be defined by a three tuple containing the index space, the field space, and what we're going to call the region tree ID for these logical region objects. You can actually see this tuple. It's mostly hidden from the users. Logical regions can be used as opaque handles, but if we actually look at logical region here, this is also in legion.h, you'll see that this class logical region has exactly three member variables, a region tree ID, an index space, and a field space that name the various components of this logical region. This is the three tuple that represents this logical region handle. And we're going to see today what it means to have a region tree ID. Effectively, this is going to be able to uniquely identify the region tree that this logical region is a part of. Okay, so coming back to create logical region, so we're going to pass in these three things, and we're going to give back a logical region handle. And in the process, we're going to see the runtime actually makes a logical region tree node for the root of this new region tree that we're going to create. Okay, so let's see how that happens. I'm going to avoid bouncing through legion.cc just because it's an unnecessary level of indirection for us to go through today. So what I'm going to do is I'm going to jump into runtime.cc, and we can look at what happens when we call create logical region. So searching for create logical region. Okay, here's our entry point into create logical region from the runtime API. Again, the first thing you'll see that we do is we're going to create one of these region tree IDs that I mentioned that's going to name a new unique region tree that all of the logical regions and subregions of this logical region that we're making right now are going to be a part of. And you can, one of the important details here is that the last time I think we looked at how we actually make these unique IDs. So region tree ID is really just an unsigned integer. You can see that type def in legiontypes.h. You guys can go look that up yourselves. But what you're going to notice is that we're again using one of these get unique operations that we looked at last week. And so you recall that what this is really doing, let's actually go look at this just to remind everyone. Get unique tree ID is effectively just iterating or just incrementing. It's taking a current value of this unique tree ID value and then incrementing it by runtime stride. And all of the different high-level runtimes across all the different nodes in the system have a different initial offset of this such that they can each generate unique ID for region trees without needing to communicate with each other. So this get unique tree ID is just effectively giving us back a new unique ID to use for when we actually need to make a new region tree ID. Okay, And jump back to get unique tree ID. Okay, so you can see the first thing we do is we get this unique tree ID, and once we've got that, we can actually build the handle for our logical region that we're going to be returning. So you see we pass in the 3 tuple here, the TID, the new tree ID, index space, and the field space that the user was creating. And from that, we've made a new logical region handle. Now we haven't actually done the work yet to actually instantiate the region tree yet, or the region tree node. So what we're going to have to do is we're going to have to down here, we're going to call into create logical region, which is actually going to go and actually make a logical region inside of our region tree forest object here. And then once we've done with all that, we can actually go ahead and return this region. In the middle here, you see there's a bunch of debugging checks and some logging information, but nothing that's super important for our purposes today. Okay, so let's actually go into this create logical region, call inside the region tree forest, and see what it does. So I'm jumping back into regiontree.cc. Okay, searching for create logical region. Okay, and so we're taking in our logical region handle here, and what we're going to do is we're actually going to make a node for the root of this this logical region tree. So again, you can see one of the things we're going to do is we're going to invoke this overloaded create node method that we saw the last time, which is used for creating nodes in index-based trees and field-based trees, or in region trees and so forth. And so what we have to do is we pass in our handle and we pass in a pointer to our parent object. In this case, since we're the root of the tree, our parent is going to be null. And we're actually going to go and make this node. Okay, so let's actually look at create node for region tree forest. Okay, so what you'll see here is we're going to do the exact same thing that we were doing for index space. Oh, I went to the wrong overloaded variant here. Let me keep going. Here we go. Here's the one for logical regions. Okay, and you'll see that this one is a little bit more complex. And we're going to talk a little bit why this is slightly more complex than the overloaded ones that we saw last week for index-based trees and or for index-based nodes and index partition nodes. Remember those ones were up here. We were looking at those last week. And effectively, all we do is we take a lock on this map of index nodes. We check to see if someone, or we make the node. We take a lock to see if someone has already made it. If they already made it, we can delete the little one that we just made and return the one that was already made before. Otherwise, we add ourselves to the set, and then we add ourselves as a child to any parent that we have, and we're done. So that's pretty simple for index space and field spaces. You'll see that the one for logical regions is a little bit more complex. So one of the first things that we want to do is one of the requirements for making a region tree node. You can see here, here's the call to actually try to create the actual node. So that's where we do our construction. You can see there's a new operation here to build a new region node here, and we'll go look at the declaration for region node in just a minute. But you'll see one of the things that we want to pass in is actually an index-based node and a field-based node associated with this logical region node. We didn't talk about the creation of field spaces, but they mirror the creation of index spaces very similarly. And we have separate field space nodes to represent individual field space objects. One important detail is one of the nice things is that field spaces, unlike index spaces and logical regions, is that they don't get partitioned in any way. They're effectively one-off objects. And they don't have any parents or children or stuff like that. So they're actually a little bit simpler, which is why I'm not going to show them. But they operate almost exactly the same as the creation of index spaces and logical regions. You can actually see the creation for field space nodes right here immediately above where we are now. Okay, one of the things you'll see is that in order to make a region tree node, what we want to do is actually have references to the index space node and the field space node of which this region tree node is going to be a part of. And what you're going to see is we're going to have names for these things. And we're going to call the index-based node what we call the row source. And then what we're going to call the field space is the column source. And this actually comes from sort of a thinking that we have inside the Legion runtime where we like to think of logical regions as sort of representing tables. And so an index-based node represents the key space for this logical region. So we call those the rows, just like a relational table. And then a field space represents all the fields across the top of a logical region, and therefore it's called the column source. So we call these row source and column source. It's just a naming convention. But whenever you hear rows, you should think of index spaces, and whenever you hear columns, you should think of field spaces. Okay, so what you see is that we actually invoke get node on both of these different operations in order to, or both of the index space and the field space required for this logical region in order to get pointers to them. And then what we do is when we create our region node, we're going to pass in the pointers so it knows how to reference its row source and its column source when it actually gets constructed. Okay, once we've made our region tree node, what we're going to do is we're going to try and register it. So again, we're going to do the same trick. We take the lookup lock to see if we've already made this logical region. So we're going to look for the handle on the set of region nodes. If we find it, then we know that somebody else already made it, in which case we can delete the little temporary one that we made and return the one that already existed. Otherwise, we're going to register ourselves in the map of region nodes. Now, here's one point. You'll notice here there's an extra call that occurs before we actually register ourselves in the map. What we're going to do is we're actually going to update what we call the set of contexts. So unlike on this region tree node, so unlike index-based and field-based nodes, logical region tree nodes are actually responsible for storing a bunch of different state associated with which tasks are executing and using different logical regions as part of their execution. And we refer to this various state. There's two different variations of the state, both a logical state and a physical state associated with logical analysis and physical analysis. And what you'll see is that we actually need to reserve some of that state here. And that's what this call is going to do. And we're actually going to look at this in more detail later today. We're actually going to see, how do we reserve this state for region tree nodes, and what does it look like? But just remember this call here. We're going to come back to it a little bit later today. Okay, so once we've updated our context data structures, then we can register ourselves in the map, which is actually going to we can put ourselves in the map. And then if we're on a top level region tree, we're actually going to do one extra level of registration, which is we're actually going to register this as a new region tree, as the root of a new region tree for our runtime to track. So there's a special data structure called tree nodes, which stores the roots to all the logical region trees that we know about. And you see that only happens if parent is equal to null. One other thing that we do is if we actually register ourselves with our column and row sources. So if we're the root, we're going to tell our field space that we're the top level logical region that's using that particular field space. And then we also tell our row source that we're a new instance of that particular index space. So we can always reference all of the different region trees that are instantiations of index spaces, or all the different logical region nodes that are instantiations of particular index spaces, and so forth. And finally, if we're not a parent, we have to add ourselves as a child of the particular logical region. Okay, so that's how we create nodes for logical regions. One of the things that you're going to find is that we actually employ a similar system for creating logical partition nodes. So this is the final overloaded create node method, this one right here that we're looking at now. This one is for creating logical partition nodes called partition nodes. And so what you see is it actually has a very similar structure to the one that we just looked at, including needing to reserve these context objects, which we're going to look at momentarily. Okay, so that's how we create logical regions. One important detail that you should be aware of. Let's jump back here to legion.h real quick. If I come back up here, look at legion.h, you'll notice that there is no create logical partition operation. So if we search for create logical partition, we don't get anything. Instead, what you'll remember, for those of you that have used the Legion API, you'll notice that there are a bunch of create index partition calls. Here we go. And these are how we create partitions on the index-based tree, but we don't have corresponding operations for creating logical partitions inside the region tree. And of course, the reason for that is that for each one of our, once we instantiate a logical region from a particular index space, all of the index partitions of that index space for that logical region already exist on the logical region tree that we just created. So if you've already taken an index space and partitioned it up a bunch of different ways, and then you make a logical region from the root of that index space tree, you already have logical partitions for all of those different index spaces. So that's why we don't provide explicit create index partition methods. Instead, what we want you to do is partition an index space tree, and then the logical partitions will automatically exist. And of course, there's a bunch of different methods for accessing these different logical partitions. So if I search for get logical partition, you see there's a couple of different methods here for getting logical partitions, either by specifying a corresponding index partition handle, by giving a particular color of the logical region to get the color partition, or by giving the actual index partition, the field space, and the region tree ID for the partition that you want. So just to show you how this actually creates a logical partition node, let's actually look at this get logical partition call. I'll jump through runtime.cc, or I'll pass legion.cc. We'll jump into runtime.cc. We search for get logical partition. Okay, you see it does a little bit of checking, and then right away what it does is it turns around and invokes the region tree forest, asking it to get this logical partition handle. Okay, so let's jump into regiontree.cc. Searching for get logical partition. For some reason it is not being highlighted properly. Okay. So what you'll see is that in some cases, it's very easy to just, create the handle and return it. But in other cases, what we want to do is actually get the node for one of these logical partitions and actually create it. And so what you can see is that, so what we're doing here is actually employing, a very interesting technique of the Legion runtime, which I think I touched on the last time, but what I should actually call out in detail here. What you see is that in some cases where you can just automatically build the handle right away based from the components that were passed in. So in some cases, we can build a logical partition based on the parent tree ID, the handle, and the parent field space. In other cases, we actually have to go look some nodes up and actually find their children and return the right objects to actually be able to create one of these handles. Now you'll notice that there's a very important distinction here between logical region trees and index-based trees. So we looked at index-based trees last week. Whenever we returned a handle back to the app, one of the invariants that we were maintaining was that whenever we returned a handle back to the application, we were making sure that that index-based tree node, whether it was an index base or an index partition, already existed in the index-based tree itself, inside the internal representation that the runtime had. So any calls that came into the runtime that passed in a handle, we knew we could always go and get that node and have it automatically instantiate itself. You'll notice that we're doing something different here with the logical region tree handles. In some cases, like for example right here, we're just creating the handle and returning it right back to the application, and the application actually now has a handle for a logical partition that we haven't actually created the node for yet. And this is a very important variant that I mentioned last time, which is that we support lazy instantiation of the logical region trees. And the reason for that is that we want to eagerly instantiate the index-based trees because we need to be able to have a way of naming them and storing all their necessary information. But we can lazily instantiate the logical region trees because they're based on just field spaces and index-based trees. So we don't need to explicitly enumerate all their nodes. We should be able to create nodes on the fly as we need them. And so the place to actually see this, you can see here we're just returning handles without actually creating nodes. You can see the place that we deal with this is in the get node calls, the overloaded method for returning different kinds of nodes inside of our region tree. I search for get node. We have a bunch of different overloaded versions. We have index space, index partition, fields, and here's the one for logical regions. And so what you'll see is that this one is actually a little bit more complex than these ones that came before. Like, for example, getting a field space or getting an index partition node, you just look up you take the lock, you look it up in the table, and you should be able to find it. If you don't find it, it's an error. But for logical regions and logical partitions, that's not necessarily the case. So for example, in this call for getting the logical region, what you'll see is that the first thing that we'll do is we'll check to see if the node already exists. If it does, we're going to be done. So we take our lock right here, lookup lock. We only need read-only mode. We look up in the region tree nodes data structure, trying to find our node. if we found that we're done. Otherwise, what we're going to need to do is actually go and make so we can actually have the node for this corresponding that's been lazily instantiated. So what we can do is we can get the corresponding index-based node, and then what we can do, we can build the handle for our partition. Then we can get our parent partition node, which allows us to have the pointer to our parent. And then from that, we can call create node, which is going to actually allow us to get to actually make this node for this particular logical region. And so this is how we effectively do the lazy instantiation of the logical region trees on demand as these different nodes are necessary, and allows us to pass back these handles to the application without having to eagerly instantiate whole bunches of region trees that we might ultimately not need. Okay, so that's a very important detail of how the high-level runtime is actually creating these logical region trees, and how they differ a little bit from how the index-based trees operate. Let's actually take a diversion now. Let's actually go look at where these region tree nodes and these region nodes and partition nodes are created for the logical region trees. Are declared. We'll look at where they're declared, and then we're going to look at how some of their data structures, and specifically these context data structures that I've been referring to, get instantiated. Okay, so I'm going to jump back here to regiontree.h. Okay, we're going to search for class region node. Okay, here's the declaration of a region node. What you're going to see is that both region nodes and partition nodes extend this base class, region tree node, which I believe is actually declared right here immediately above the region node class. You can see there's a lot of methods for all the different kinds of analysis. Yeah, so here's the class region tree node. It provides the base class for all nodes inside of the logical region tree. You'll see that there's some virtual methods in here these are pure on this class, but they're not pure on region node and partition node. So region node extends region tree node. You can see declarations for all of our various methods that we need to support. And then down here at the bottom, we have all of our basic data structures that are particular to region tree nodes. We're going to go look at data structures on general region tree nodes in just a minute. So you see we have a pointer we have our handle that names the handle for this logical region node. We have a pointer to our parent partition node. We have a pointer to our row source, to our particular row source node, which is an index-based node. And then we have lists of, or maps to track, which of our children are valid. So the color map is all of the children that we've ever seen, and then the valid ones are the ones that are still valid. We'll see some example uses of those data structures probably at a later point in time. And you'll see this is the declaration of partition node. It also extends the region tree node, has a whole bunch of methods, many of the same ones, just doing slightly different operations. And it has a bunch of different information about this partition as well, like its handle, the pointer to its parent region node, a pointer to its row source, index partition node, and again, color maps and valid maps. Okay, and because both of these classes share the same parent type, this region tree node class, this is the region tree node class that we looked at. You'll see down here at the bottom, there's some very basic data structures that are also contained within these for both region nodes and partition nodes. So you can see one of the things that we have a pointer to is the enclosing region tree forest. We call this the context. Context is an overloaded term in this case. You should not confuse this with the context that I was mentioning earlier. Just think of this as the pointer to the region tree forest that these logical region trees are. You can see that we also have a pointer to our column source, which is the field space that names the set of fields that are valid on this particular logical region or logical partition. You're going to see we have these node masts, and we're going to hopefully look at these later today. These are going to track which nodes inside of our big system, inside of our distributed system, know about the creation and deletion of different logical region nodes, logical region tree nodes. You see that we have a reservation, which is going to provide our atomicity mechanism for accessing different parts of these data structures. You'll see that these are probably the most important data structures on logical region tree nodes. And you can see what these are tracking are the set of what we call logical states. and physical states for each of these different region tree nodes. And so this is the most important data structures for these region tree nodes. The reason for that is these data structures are going to store all the state for various different tasks which are traversing the logical region trees for doing both logical and physical analysis. Now, what's important to realize is that the reason that we actually have these data structures, and what you're going to see is I've called these Legion stacks, but they're really just data structures allow us to have to allow these data. We're going to look at this briefly, but this is just a data structure that allows us to grow these logical state and physical state data structures without having to reallocate them. And you see they're supported by a maximum number of contexts and a number of default contexts they initially support. And so this is going to allow us to create these logical states, potentially to allocate new ones without needing to move the existing ones. Now, the reason that we want this kind of property is that it's important to realize that you'll notice that we only make one copy of every logical region tree inside of every runtime instance. So every runtime has one of these region tree forest data structures, all the logical regions, and index spaces and field spaces and so forth. And all the different tasks, no matter what parent task they're a part of, are going to be doing their analysis over this same data structure, these same logical region trees. So it's possible that we might have many tasks running in parallel on the same high-level runtime instance, all doing analysis, possibly with different parent tasks across the same region tree data structures. And so what these two logical states and physical state data structures are going to represent is the state of the analysis for various different parent task contexts as the analyses are being performed. So what to do is actually have multiple tasks doing their analysis over these region trees at the same time. And then different state associated with each of these different region tree nodes are stored in these different logical state and physical state data structures. And so the reason we have a little bit of special kind of data structure here called this Legion stack data type is that it's allowing us to mutate the size of this data structure without actually needing to reallocate these logical state and physical state objects in case some other task is doing analysis over the same region tree at the same time. Okay, so let me formally just say what these contexts are, just so you can have a clear definition in your mind of what these contexts are and where they get created. And then what we'll do is we'll come back here to look at these Legion stacks, and we'll actually look at this logical state and physical state object, just so you can see where they're declared. And then we'll actually talk a little bit about how we grow the set of logical and physical states during actual instantiation or how while analysis is actually possibly going on for other tasks. Okay, so the concept of a context is a very important one inside of Legion. And the idea of a context is that for every time that we start a task, which is not a loop, we want to create a context object that declares, that says that this will be, that this task when it is running is going to define a context. And then any child tasks or child operations that it creates will have to map within this context. And what this context really is just a handle that's going to be used to index into these logical and physical states to declare exactly which physical state or logical state and physical state objects to access when doing the analysis over these region trees. Let's actually look at where these contexts get allocated, just so you can see where they live and where they get allocated. So if I jump back here, let's see, probably want to go into runtime .h right now. And so if I search for region context, you'll see that there's a little class here called region tree context. So these contexts are actual real objects, but they're actually very simple things. In fact, all they do is they store just a single value, which is an integer that says, which is a context ID. And all that context ID says is it is a way of indexing into the logical state and physical state data structures that we saw on region tree nodes. But we do have these region tree context objects, and we make them explicit, so you can track them around as as they move through the runtime. And what you're going to see is that the way that the runtime works is that every high-level runtime is going to have a little pool of these region tree context operations on its local node. And whenever a task actually starts running on this node, we're going to ask to allocate a context. And then whenever those tasks are done running, we're going to free those contexts to make them available for other tasks that are going to run later. So for example, if I search for get available, let's see if I can find the, trying to remember the name of the call here. See if we can find it. Maybe it's allocate contexts. There we go. Okay, so what you're going to see is there are two methods here. This is on the this class right here that we're looking at, just to show you. Is a big class because it's the runtime. This is actually the class runtime. The runtime is going to maintain a pool of these region tree context operations, and then when tasks start, we're going to call allocate context and pass in a pointer to the task, which is going to assign this task a context to use. And then when the task is done, it's going to be responsible for freeing its context. Let me just show you what those two methods actually look like. So we jump into runtime.cec here. And we search for allocate context. What you'll see is that this runtime, it says, first thing we do, we take our lock on the set of available contexts. If it's not empty, we can pull one off the front and assign it to this particular task. So we call task assign context. We then pop it off the front of the stack. At this point, we can return because we're done. So as long as we have context floating around, we can always give them out to tasks for them to use. And that's going to be the index that those tasks use whenever they're doing traversals, or whenever operations they launch are doing traversals over the logical and physical region trees. That's going to be how they index into those logical state and physical state data structures. Now, if we fail to get a context, we actually want to actually try to make one. Now, this is an important property of, now one of the important things that we do is we actually set currently a maximum number of contexts that can be declared. And we're going to see where we use that inside of the dynamically allocated data structures inside of the Legion stack operations. Okay, so what we're going to do is we're going to contexts. In fact, we're actually going to make a bunch of new contexts. Once we are taking the time to try to double the number of contexts that we have available, just so that we can avoid having to do this operation. It turns out that this context allocation is actually kind of expensive, and we're going to see why that is. So one of the things that we'll do is we'll increment the total number of contexts. So we do this as a little atomic operation. And then what we do, there's a quick check here to make sure that we haven't exceeded the maximum number of contexts that our have actually requested. And then what we do is once we've incremented that context size, we actually tell the region tree first that we actually need to resize all of the different logical state and physical state data structures on all the different region tree nodes. And that's why this operation is expensive. It's because what we want to do is we want to make sure that all of the region tree nodes already have their logical state and physical state allocated for all of the different contexts that they're going to potentially need. Okay, so let's actually look at this briefly just to see what this resize node context does. And we see we're giving it a new number of contexts to actually allocate. So if we jump into region tree forest.here.cc, I remind myself just a resize node context is the call that we are looking for. Okay, searching for resize node context. What you see is that we take a read-only lock on the lookup for all of these different operations. And what you'll see is that we then iterate over all of our region tree nodes and all of our partition nodes and ask them to reserve new state up to the total number of contexts that are actually required on this particular region tree node. If we go look at reserve contexts, Here's the call for logical region for any arbitrary region tree nodes. And what you see is that we add onto the back a set of logical states and physical states onto the existing set of logical states and physical states. And so what this guarantees is that once we hand out this context ID, we know that any context ID that comes into all of these logical region tree nodes is going to have it automatically already be instantiated to actually track all of this different, or actually be able to automatically index into these logical state and physical state data structures so that we can access them without needing to do any allocation on the fly. Okay, so the invariant that's being maintained here, just to recap, is that once you create a region tree context, what you should guarantee is that every single one of the region tree nodes that exists already has state allocated in the logical state and physical state data structures to actually be able to index with those particular context IDs. Okay, let me just show you briefly where the context allocation actually occurs, so you can tie it back to something that we saw earlier. And then I want to go look at those logical state and physical state data structures. So just to show you where the context allocation actually occurs, if we go into legion tasks.cc, we're going to go look at is actually the launch task method. So I search for a launch task. You remember this is the method that we use for launching all of our application level tasks to actually go and do operations, or go and launch tasks that are actually running on real processors. And what you'll see in here is that there's allocate context call. So here's the case where we're actually calling the runtime to actually allocate this context. You'll see that we only have to do this. We only have to allocate context if this task is not a leaf task, or it has some number of virtual mappings. In which case we do need to have it, because we might potentially be doing inline mapping operations and so forth. But if either of these two things are not true, then we actually can skip allocating a context. So this is exactly where that call to allocate a context occurs. It occurs once we're going to launch the task. We know we need to allocate the context. And if we actually search for free context in here, you'll see that there are various places. Here's the case for single task. So once the task is done executing, it starts to clean itself up. Notice this is occurring in the deactivate call. So once the task is being deactivated, it can actually free its context and give it back to the high-level runtime so that it can be reused for other tasks that come along and need it in the future. Okay, so hopefully that ties things back to where you guys have seen things before involving task operations, so you know where contexts get allocated and where they get freed up when they're done. Okay, let's actually go look now briefly at these logical state and physical state data structures, because they're going to be the basis of things that we're going to be doing, the kinds of analyses that we're going to be looking at in the future. So I'm going to go into regiontree.h right here. We're actually going to look for those two types of states that we are looking for. So the first kind is actually, I believe that these are structs. And I am correct. Okay. Here's a declaration for the struct called logical state. And what you're going to see here is that this logical state data structure is going to contain information or data structures that we're going to need when we're going to do our logical dependence analysis. So what you're going to see here, there are actually three things that we need here primarily. The first set of things that you'll see here are a set of what are called field states. You'll see that these are big, complicated type declarations here. That's effectively a type declaration. The real thing to take away from this is actually a wrapper around an STL list. I'll talk about why we need these wrappers in a minute, but anytime you see Legion list, then this just means that this is an STL list wrapped with some extra information. I'll mention why in just a moment, but you can see we have three lists here. Just to show you briefly, you'll see that there are a couple places where you'll see this in the high-level runtime. You'll actually see that there are Legion maps. There are also Legion sets, and I believe there are Legion decks. So any place that you see these type declarations, just assume that it's an STL data structure with some additional stuff, like maybe a different allocator or so forth. So coming back to struct logical state. So what you see here is we have 3 STL lists effectively. The first argument to this template is the type. So what we have here is we have a list of field states. And what this field states data structure is going to track is which children are going to be open below this particular logical region tree node. So which children are open, and we're going to talk about what that means when we go to look at logical dependence analysis probably next week. So we're tracking the field state of all of which fields are open on each of our different children. And then we have 2 other lists, both of which are tracking what are called logical users, which again I think we'll look at in the future. But these logical users are naming tasks and other operations which are accessing this particular logical region or logical node in the logical region tree. And what you see is that we have a set of current users, and I'll talk about what that means later, and a set of previous users. And we'll see how those 2 data structures get used as part of the logical dependence analysis a little later. And then finally, we have one of these things called a field mask, which I think I will also get into later. But this one is used for tracking where simultaneous coherence has been used inside of this logical region tree. And again, this will be a topic for a future. But effectively, what this logical state data structure is doing is it's tracking all the information necessary for doing logical dependence analysis within a single context. And so where these logical, and those Legion stack data structures that we saw earlier that declared a set of these logical states is effectively providing the data structure that stores a set of these state objects that can be indexed using a context ID. Okay, so that's logical state. You'll also notice that we have a physical state data structure, and it contains a little bit more some other data structures that we're going to need for doing our physical analysis. Things like, a field mask tracking which fields are dirty, another field mask tracking which fields we have reductions going on in, and some other important properties of this physical analysis. You can again see we have some instances of these wrapped Legion data structures. Now that we've actually seen logical states and physical states, I'll just mention what these data structures are, just so you're aware of what's going on here. What you'll see is that in some cases, what we want to do is we actually want to track the allocation of various or memory usage of various parts of our runtime states. We have some logging, some tracing infrastructure to track a lot of our allocations of some of our bigger data structures. Logical states and physical states tend to be involved in usually some of our bigger data structures. We want to track all the memory usage associated with them. So what these data structures are doing is they're wrapping standard STL data structures, but we're passing in a flag that's going to be passed to a custom allocator inside of the STL data structure. And that custom allocator will just do the normal type of allocation using new and delete. But what it will do is it will also, when certain macros are enabled, it will actually tell Legion to actually trace the memory allocation to know that a certain amount of memory has been allocated with this particular tag. So then what we can do is if we're seeing memory leaks or we're seeing large allocations of memory, we can actually figure out which data structures are responsible for producing the excessive memory usage that we're noticing. And so really, this is just wrapping a custom allocator that's getting passed to an STL data structure. And since those, tend to be rather verbose to write out, we wrap them inside of these other kinds of types. If you're wondering where these are actually declared in Legion allocation.h. I can actually show you guys where those are. You come up here to Legion allocation.h. What I think is they are actually all the way at the bottom here. Yeah. So you'll see that there are these bunch of different templated structs that for naming Legion sets and Legion lists and Legion deck. And you see that they take a type and an allocation type. And then what they do is we use a custom allocator called the Legion allocator that is used to actually do the tracing for a particular allocation type. One of the other important properties that these various Legion data structures support is that they actually allow us to do alignment of these types that are going to be passed into these various data structures. You can see in some cases here, we have different variations of the set, depending on whether or not we want our allocator to do alignment. So we can pass in false to do aligned, or true to align to actually do specialized alignment for this particular type. The reason for that is that we'll actually see some cases a little bit later on where we're actually going to need to require 32-byte alignment for various objects that we're going to be allocating as part of these data structures. And so when you declare these Legion sets, you can say whether you want the tracked version, which is just saying whether or not to track memory allocation. You can say you want the aligned version, which only does alignment but doesn't track anything. Or you can do track aligned, which is both tracking the allocation inside this STL data structure as well as making sure that the type allocations are going to be aligned on the proper bound for this type. And we have that for pretty much every single kind of data structure that you need from the STL. We have sets, lists, decks, vectors, maps. And if you need other ones, it's very easy to add them right here using the existing building blocks that we have. Okay, jumping back to region tree.h. Let's see here, all the way down. Okay, we're looking at struct physical state. Okay, and so, yeah, I guess just wrapping up. So we have some various different data structures that we're going to be used for tracking the physical state of various region tree forest objects. And I guess the last thing to look at today probably is just those Legion stack objects, just so you can see how they are, how they're allocated and how they work, just so you can be familiar with what they're doing when we actually go to use them. Okay, so here's this Legion stack class. You see it's a very simple class. It has some very basic operations. It actually works very similar to some STL data structures like a deck. And the idea is that we want to be able to allocate new entries inside of these Legion stacks. We effectively want to grow this stack without needing to reallocate the existing elements that have already been allocated inside of these Legion stack operations. The idea of this Legion stack is really just, but we still want to, the other important thing that we're going to want as part of the properties of this Legion stack, in addition to being able to grow its allocation without having to reallocate the existing or copy the existing elements inside the data structure, the other important thing that we want is we want these lookups that are going to be done for these Legion stack objects to be very fast and efficient. And this is going to be necessary for being able to do fast lookups for when we go to access those logical state and physical features as part of the analysis. So you can see we want our access time to these to be effectively constant. Okay, so the way that these Legion stack operations work is what we do is we have a pointer to a buff. Well, actually, what this is really is it's an array of pointers to allocations of these entries of type T. The way to think of this is just an array of arrays. So this is an array of pointers that are each going to point to an array of the elements of type T. And so what we're going to do is we're going to have at most max size divided by the increment size, number of pointers. And then every time we need to do a new allocation, we can just increment this. We can just add a new buffer to this set of data. Or what we do is we'll allocate a new array and add to the next null pointer inside of this buffer to increment, to add to a new allocation. That probably wasn't the best description, so let's actually go look at the code. It's much cleaner when we actually look at the code. Okay, so I jump into regiontree.cc. If I search for Legion stack, actually these are templated, so they're actually probably going to be, actually am I in the right place? I am. I know that this code is all the way at the bottom, so we can just jump down here. Yeah, here we go. Okay, so what you'll see is that there is actually the place to look at here first is this append operation. So what you'll see is that we have if we have existing entries inside of our operation, we can just immediately add to our existing allocations. Otherwise, what we need to do is we've already allocated in our some number of objects that are free, so we can decrement that from the append count. But if there's still things remaining, we're actually going to need to allocate a new array to actually be able to handle the new set of operations that we're going to be, or the new set of entries inside of the stack that we're going to be adding. So what we do is we compute how many new arrays we're going to need to make based on this append count that we have left. We can allocate these new arrays. So what you see is for every one of these entries in this pointer buffer, at our previous buffer size, we keep adding on to it. We allocate new arrays of increment size. So whatever increment size is, that's how much each one of those new array sizes are. And then what we can do is we can decrement, or we can set our values for remaining in buffer size once we're done. So what we're doing is effectively we start off, maybe I should have pointed this out earlier, the place where we start off at is we have a new buffer of pointers that are effectively all null. And we haven't allocated any of them, or we've allocated exactly one to begin. So we've allocated pointer buffer 0 of a new array, but all the rest of the entries in this pointer buffer are all empty. And what we want to do is, as we need new entries, we can go ahead and allocate new arrays of size, increment size. And that allows us to allocate new entries inside of this data structure without needing to actually resize or reallocate any of the existing entries. Longer term, what I will probably be doing is migrating these data structures to look more like some of the dynamic tree allocation data structures that you see in the low-level runtime for handling events and reservations that Sean, I think, has talked about before. If not, we'll definitely be getting those soon in a low-level talk. But that'll allow actually us to hopefully get rid of some of the restraints on max context that we have today. So that'll allow that to be an unnecessary part of the configuration of the Legion runtime. But for now, this is what we have, and it seems to be pretty well for most people. Okay, so I'm almost out of time for today. So what I'll do is I'll open up the floor for questions. And if nobody has any, I think Sean will be back to talk about the low-level runtime on Wednesday. And then I will be back next week. And hopefully we'll be able to start talking about logical dependence analysis next week. Now that we've actually looked at some of these data structures in detail, we can actually start talking about how we're actually going to use these region tree data structures to do dependence analysis. Okay, any questions? No questions. All right, I think we are done for today. We'll see everyone next time.